We've all seen waves in one form or another, be it waves on the seashore, waves in a slinky, or even by a hip hop dancer. In all these motions, we observe that there is something which is moving. Now, what exactly is that something is one of the things we want to explore today. Also, what exactly is wave motion and how do we describe it is another part of our exploration. Now, we at Aakash BYJU'S strongly think that seeing is believing. So we are going to explore wave motion with the help of this simulation. Now this simulation has been developed by PhD Colorado. It's completely free. Link is in the description. Do play around with it after the session. So what you see here is a string, and the beats are the representation of the particles of the string. Let's say there is a bell which is hanging from this window. I'm standing over here and I want to ring the bell. Now one of the ways I can do it is that I can walk all the way up here and then strike the bell. If I strike the bell, I transfer energy to the bell and the bell is going to ring. Now notice that I'm carrying energy in my hand and I'm taking this energy all the way up to the bell along with me and then transferring the energy to the bell. So in this case, there is a bulk motion of the particles or the net displacement of the particles being me, which are carrying the energy with them. So this kind of motion is called bulk motion. But I'm lazy. I don't want to walk all the way up there. So what I can do is I can simply push this button. Now if I push this button, you see that there's a bump created in this string. You can also create a bump. Just take a string and snap your hands up and down very quickly. Now when this bump is created, we have basically introduced a disturbance in the string. And this disturbance carries energy with it. Now this disturbance is going to travel all the way along the string and it is going to strike the bell. So we have managed to transfer energy from the left end of the string to the right end of the string. But the most important thing is that if you focus on one of the particles, just focus on this green particle. This green particle only goes up and down. There is no net displacement or bulk movement of any of the particles. Still the energy is being transferred. This kind of motion where the disturbance or energy propagates without the bulk motion of the particles is known as wave motion. So we have established that in wave motion, there is no bulk movement or net displacement of the particles, and the thing that we see moving is the energy or disturbance. Now let's move to a deeper understanding of waves. For that, I'm going to choose y-axis like this, and I'm going to choose the x-axis along the string like this. Now what I want to do is I want to create the waves on the string, and for that, this is the simulation I am running. Okay, now this is a waveform we are much more familiar with. Now listen to this statement very carefully. In a wave, a property changes periodically with space and time. Let's try to understand this. Now if we look at this wave motion, what is the property or what is the quantity that is changing? Now you can notice it is the transverse displacement or the displacement of the particles along the y direction which is changing. So the property here is the transverse displacement of the particles. Now let's observe their variation in space. In space meaning along the x-axis or along different points on the x-axis. So let me pause it over here. Okay. And what I want you to do is I want you to concentrate on two particles. First is this particle over here. This has a displacement of 0 and you can see that it is going up. Now let's move along the string and we find another particle over here. This particle also has 0 displacement, but you can observe that it is going down. This is not the same motion. These two particles are going in opposite directions, hence they are out of phase. Even though the displacements are the same, but we cannot say that it is the same motion. Let's move further down the string and reach this point over here. Now this also has the same displacement 0 and you can notice it is also moving in the vertical upward direction, which means the motion of the particle over here has been repeated by the motion of the particle over here. And then as we move along the string, the motion of the particle over here is again the same. So the motion of the particle is repeating as we are moving along the x direction or in space. And the minimum distance between two such points is called, you know it very well, it is called a wavelength, and it is represented by lambda. Now in low classes we have understood that the wavelength is from crest to crest, or it is from trough to trough, but we can extend that definition now. Any 2 points which are behaving in the same manner, or we can say they are in phase, the shortest distance between them will be called a wavelength. Okay, so you see the property is repeating itself periodically in space. Now let's observe how this is achieved in time. Okay, for that I'm going to get rid of these things. Let me quickly get rid of these things. All right, and I'm going to run this simulation again. Okay, let's go. Now what I want you to do is, I want you to take a mental picture of this shape of the string. All right, done? All right. Now as the wave progresses, the shape of the string changes. The shape of the string is changing. The shape of the string is still changing. And I'm going to pause it over here. Now just recall this picture. The shape of the string has been regained, which means that the displacement of all the particles on the string, the motion of all the particles on the string has repeated itself after a certain interval of time. And this keeps happening and happening and happening. The shortest time interval is called, you know it, the time period. And the frequency is defined by 1 upon time period, which means cycles per second. So now you have understood how this property, the displacement in the y direction, varies periodically with space and time, and this is what is a wave on a string. Now in sound waves, the property that changes is the change in pressure. In electromagnetic waves or in light, the property that changes periodically with space and time is the electric and magnetic field. So now you have a good understanding of what are waves. Now let's move on. Next, how do we describe a wave? We describe a wave by the wave equation, which is the variation of the property with x and t, which means for any position and at any time, if I know the value of that property, I will be able to describe the wave completely. I will know everything about that wave. But how do we arrive at the wave equation? For that, we need to understand what dictates the formation of a wave. So for that, what I'm going to do is, I'm going to move the left end of the string and I'm going to create a waveform. So the left end of the string can go something like this, and a kind of waveform is generated. Or what I can do is, I can move this left end in a different manner, something like this. And what I have created is a box type waveform, haven't I? Or I can also go completely berserk, and the waveform is also going to be very random. So what you observe here is that the left end of the string, the way it is moving with respect to time, is something that is going to dictate the wave formation. So let's try to understand this more formally. And for that, again, I'm going to take the y-axis like this, and I'm going to take the x-axis like this. And I'm going to generate a pulse over here and pause. Now this disturbance that has been created is right now at x is equal to 0. And let's say that this pulse travels along the string with a speed v, which is called the wave velocity. Now this disturbance is going to travel along the string, and at certain time, let's say the time right now is t, it has reached the position x. Now the wave has traveled, or the pulse has traveled a distance x, and the speed is v. So how much time has it taken? It has taken a time t naught is equal to x by v. Now what I can say is that the displacement of the particle at x is equal to 0 with respect to time is a function. And let's say that function is f comma t. So basically how the left end is moving with respect to time, that is being described by the function ft. Now listen to this very carefully. Can I say that the displacement of the particle at x right now, that is at time t, is the same as the displacement of the particle at x is equal to 0, which is the left end, but not right now, at a time x by v before. So the time right now is t. So at time t minus x by v, this displacement would be the same as the displacement of the particle at the left end, or x is equal to 0. Let it sink in. Let me say this again. The wave has traveled a distance x. The time it has taken would be x by v. Now the displacement of the particle at x and time t is going to be the same as the displacement of the particle at x is equal to 0, but at a time x by v before, which means at a time t minus x by v. And this function we have just defined. It is the same function ft, which means we can say that y xt is simply going to become f t minus x by v. And there you have the wave equation. Now notice that in this case, the particle was moving in the positive x direction. Now what happens if the particle is moving in the opposite direction? Let's try to figure that out. Now for that, first let me get rid of all of this and let me reverse the direction of the pulse. For that, I'm going to use a loose end. Why does it happen? That is something we're going to discuss later. But now you can understand that the wave is moving in the opposite direction. Let me again draw the y-axis and x-axis. Now right now, the position of this particle is x. Okay. The wave velocity is v. So how much time is this disturbance going to take to reach x is equal to 0? It is going to take a time t naught is equal to x by v. Distance divided by the speed. Okay. Now can I say that the displacement of the particle, which is at x and at time t is the time right now, will be the same as the displacement of the particle at x is equal to 0, but at a time x by v later. So right now the time is t, so the time later would be t plus x by v. And we already know what this function is. So y xt simply becomes f t plus x by v. And that is how we find the wave equation if the wave is traveling in the negative x direction. So if I have to summarize all of this, if we know ft, that is the displacement of the particle at x is equal to 0 with respect to time, all we have to do is substitute t with t minus x by v if the wave is traveling in the positive x direction. And if we know ft, all we have to do is we have to substitute t by t plus x by v if the particle is moving in the negative x direction. And with that, I'm going to have my wave equation and I can describe everything about that wave. Now is the time to apply this to a very special kind of wave. Okay, so for that, let me get rid of all of this and let me set up the wave. Now, how the left end is going to move is a very special function. That function is an SHM. Yes, that is a simple harmonic function, which means ft is defined as what? Ft is defined as a sine omega t, something which we already know. This is SHM. So what is happening is that the left end is going to perform an SHM. And with this phasor moving, you can understand that this is an SHM. And when it is performing an SHM, you see that you have a sinusoidal kind of a waveform. And that is the kind of waveform which we have to study extensively. And now you understand why it is a sinusoidal waveform, because the function ft is sinusoidal. Okay, so we know that the left end is performing SHM. So the equation is a sine omega t. How do we get the wave equation? Very simple. The wave equation yx comma t will be equal to, now all I have to do is a sine omega, and in place of t, I have to substitute t minus x by v. Do you agree? Because the wave is propagating in the positive x direction. Now I can write it as a sine omega t minus omega by v into x, or I can write it as yxt is equal to a sine omega t minus kx. So we've defined a quantity over here which is omega by v. This is equal to k. K is called a wave number. More about wave number in a later session when we talk about interference. But right now, let's understand this quantity omega by v is called k, the wave number. So now you have the equation of this wave, a sine omega t minus kx. Now let's try to understand how these quantities are related to each other and what is the meaning of all these quantities. Okay, so I'm going to get rid of everything and I'm just going to retain this a sine omega t minus kx. Now notice, what is A? A is the amplitude. This is the amplitude of the wave, which means that the maximum displacement of the particles from the mean position is called the amplitude. So this is the amplitude, this is the amplitude. Now what has dictated this amplitude? Let's see. Now the motion of the left end has dictated the amplitude of the wave. Okay. Now notice that there is no damping. If I introduce damping over here, you will see that the amplitude is going to diminish. Okay. But I'm not worried about damping right now. There is no damping in the string. So the amplitude of the left end is A, and hence the amplitude of the entire wave is also A. Next, what is omega? Omega is called the angular frequency. So angular frequency is related with frequency like omega is equal to 2 pi into the frequency. Okay, we know this, all of this from SHM. So what you can observe here is that the frequency of the left end is the same as the frequency of the wave. Okay, so notice this particle and notice any other particle and notice how much time is being taken to complete one cycle. Okay, so observe this particle over here and observe this particle over here. Okay, let's go. And the cycle has been completed. So you can see that this particle and this particle, both of them have completed the cycle in the same time, which means the time period is the same. So the time period is dictated by what? It is still dictated by the motion of the left end of the string. And frequency is equal to time period. So the frequency of the wave is also dictated or determined by the frequency of the motion of the left end of the string. Alright, so angular frequency, we have understood what is angular frequency, we have understood what is frequency, what is time period. Okay, now let's understand the relationship between these quantities. Now let's say that the wave velocity is v. Now we know that wave velocity is given by lambda, which is the wavelength, multiplied by the frequency. So we can see that lambda is equal to v divided by f. Now if we are not changing the tension of the string, then the wave velocity is not going to change, because we know that wave velocity is given by under root of t by mu, where t is the tension. So we are keeping the tension constant. Now what we are doing is we are changing the frequency of the wave. Okay, I can do it from here. Okay, I can decrease or I can increase the frequency of the wave. So notice what happens if I decrease the frequency of the wave. You can guess what is going to happen. If I decrease the frequency of the wave velocity is constant, which means the wavelength is going to increase. And that's what you see over here. The wavelength has increased. And if I do the opposite, if I increase the frequency, you can notice that the wavelength has decreased. So with the wave equation, I can know the displacement of any particle and at any time. And using that, I can figure out what is its angular frequency, its time period, its wavelength, so I can describe this wave completely. If you enjoyed learning this way with visualization and simulations, learning the BYJU'S way, download the Aakash BYJU'S app, explore it. There is a lot of interesting stuff over there. Till the time we meet again, take care. Bye-bye.